Good afternoon, everyone. Thank you, Libor, for the kind introduction, and thank you, the organizers for inviting me, among all these selected group of speakers. I am here, so I expect to be at the level of the workshop. Today, my name is Edgar GALINDEZ. I came from the Johannes Gutenberg University here in Mainz. I am from the group of Professor Chloe. And today I will talk to you about some or last measurements of the altermagnetic properties measured, as Libor mentioned it, in hematite. That is one of the oxides candidates. So first of all, I really like to have a moment to thank you all our collaborators, especially all the people from the Chloe group that collaborates on this project. We are a group that it's not only me working on this. Also, thank you very much to Libor for all the theoretical insights and for all the help and the patience with explaining one and over what is an altermagnet, and especially to the people in Israel that brought the sample. I would like to finish thank you to the funding agencies, especially the SPIN+X SFB. So in my talk of today, I will start with hematite as an altermagnet. So that was shocking for us that hematite, well-known antiferromagnet, is not an antiferromagnet, it's an altermagnet. So that was kind of collapsing a lot of theory. That was really good from your side. Then I will talk a little bit about how we make this hematite a little bit conductive, because there is a thing that we need to measure transport properties in the hematite, and probably you know, but hematite is known to be insulating material. So we have to dope it, and then we have the conductivity of the hematite that is super low, and then when we start increasing the doping, we can reach measurable levels there. So then I will talk a little bit about how we measure a crystal direction dependent of the whole effect. So we just have different orientation of the whole bars, and then we check, and I will not do spoilers on that. I will finish my talk with some conclusion and perspectives, and I will love to have as much input as I can from this talk. So first, I deleted some slides because we have a really nice session in the morning about what is an altermagnet, and then Libor explained better than me what is an altermagnet. And then I will just briefly explain that one of the candidates for altermagnetism is the hematite iron oxide. And it's G wave, and then it has some symmetries that I will try to explain now. So the hematite is an hexagonal structure, and then so this rhomboidal center in the iron has some oxygens, and this has some symmetry if you see it from the top. So you have each atom has say 6 oxygen, and it's 3 oxygens up, 3 oxygens down. So when you rotate the sample, and then it's important to notice that these oxygen atoms are in non-centrosymmetric positions. So these oxygen atoms are the responsibles to break the inversion and the PT symmetries. And then when we rotate the sample to see better the hexagonal structure that I was talking about, so we have something like this. And then I just simplify the structure because it was too much atoms. And then we have a nice hexagonal structure that I will define my crystal lattice in this way. So we will have the A-axis when there is an iron connected with an oxygen, and then we have a mediated, an intermediate axis that is another iron, more or less here. So if we consider that I told you that we have 3 oxygens up and 3 oxygens down, we can also have a mirroring, and then we have also a 3 up and then a mirroring. Then when we do that, if you remember from the table, we will have a -3m symmetry, group symmetry. So when we we would like to have measure the altermagnetic properties of the hematite that is a candidate, but there is a small problem that I mentioned that hematite is insulating. So how to measure Hall resistivity and a Hall coefficient in an insulating material. So this is for the case of the ruthenium oxide, and then they were seeing some rising of the anomalous Hall conductivity, Hall resistance, and Hall conductivity when they have this starting to the spin reorientation transition, and then we know that we can also have like this spin reorientation transition in the hematite, and then someone in the 2014, if I'm not, in 2017, if I'm not wrong, reported an anomalous Hall effect in the hematite, but then it's like one report of some anomalous effect, and then it is a lot of people saying like, no, there is no anomalous effect on the hematite. So we were like a little bit more in the inside, and we were like, what is happening, what is the trick, and then like the percentage of doping is like quite tricky. So we dope our material with some titanium, so we dope at 1% of titanium, our material. So we grow the sample, like people in Israel grow a sample for us, we need a stoichiometric target from PLD, and then we have like some nice epitaxial thin films that I will try to show you. So we dope the hematite, and when you dope the hematite, there is some changes on the material per se. So the first change is that hematite is well known to have a Morin transition. So the Morin transition is at low temperatures, the spins are pointed up, and then at 260 Kelvin, they are in the basal plane, right? And they are a little bit canted. So when you go to the bulk value of 260 Kelvin, you go to dim films, like around 100 nanometers, you reduce this value to 200, and if you start like going down with the thickness of the sample, you can go like this temperature like really, really low. Up to, I don't know, 50 Kelvin is the lowest Morin temperature that we are measuring in samples of like 20, 25 nanometers. But then when you dope the hematite, you increase the Morin transition. And there is a lot of like nice papers about like what is happening, what is the theories about what is happening with this doping and the increasing of Morin transition, and I will not enter to the details now. The case is when you dope the hematite with SN, you have like a Morin transition of 300 for dim fields on 150 nanometers, and in our case, we have a Morin transition around 320 Kelvin. So the Morin transition is higher than the room temperature. So we will have the easy axis phase at room temperature, which is some of the things that someone mentioned it as a candidate, as a perfect candidate to be a device, right? We have like the altermagnetic properties at room temperature. So then we measure the magnetization as function of the temperature, and then we measure like some field dependence like at the basal phase and the easy axis phase, and then we have some Morin, so we define the Morin transition when there is like no magnetic moment, and then if we measure like high temperature, we have a hysteresis loop that is corresponding on the value of the bulk value. So this is important because we are not incrementing the magnetic field when increasing the doping. That's something that can happen, and when you increase the magnetic moment of your sample while doping, you will have a contribution of the normal Hall effect. Then when you have at low temperature, or like room temperature, like in the ECS phase, you don't have any hysteresis loop. You have a small contribution in the canted moment, and this we explain it and we blame a gamma phase, that it's another phase of the iron oxide that always nucleates between the substrate and the thin film. Then, okay, so we say, okay, so we have a quality in the magnetization, so we don't have extra magnetic moment, so we don't expect any other contribution than the bulk contributions, like in theory. So we just adding dopants to have like some electrons, to push some electrons to the conductive band, and then like can measure something, right? So we measure some like how well grown our samples were. So we have a high epitaxial sample, and then we measure the rocking curve. The rocking curve was around 0.07 degrees in omega, so that was like quite good. And then we measure an implant scan, like trying to identify where are the crystallographic A-axis that I mentioned. So we identify the crystallographic, like the threefold symmetry, crystallographic threefold symmetry that I wanted in my material, and then I mark it really well, the sample, where was my A-axis. Then okay, we say like, okay, so let's pattern some Hall bars and let's see if we can like see some anomalous Hall effect arising from this antiferromagnet that is not antiferromagnet, so can have Hall effect. So we observe at really low temperature some increasing, and then we, okay, this value for the increasing is also consistent with the spin reorientation on the hematite, but then you have a low it, right? Because if you're like passing from the easy axis phase to the easy plane phase, you will have some magnetic moment, and then you can have anomalous Hall effect. But then we are like having increasing the temperature, and then we increase more the temperature, and then we increase more the temperature, and then the amplitude of the conductivity was varying. That was surprising. And then in some point when we were like close to the Morin transition, we start like seeing like weird stuff. So we just go like really high to the easy phase transition, and then we have something like this. So measure this is quite tricky because to measure the longitudinal resistivity, you have to measure it with an electrometer. And then I will not bore in with experimental details to the theoreticians that are here. And then basically it's just you have to measure twice each device, and then you have to be sure that it's the same temperature. And that's sometimes a little bit tricky, like because you need like same stability and same conditions and blah, blah, blah. So if we zoom a little bit in the center, we will see that at room temperature we have like non-contribution at lower field, but at high temperature, when it's like the easy phase of hematite, we have a jump that is in the same size that the magnetic moment. So this effect we are not interested in. We are interested in the other effect that was raising. So we will have these jumps here, and then we are interested in how these jumps are behaving. So we try to we define the critical field as the maximum slope in this change, and then we plot this critical field as function of the temperature, and this, believe me, this fits into a Landau theory. But it predicts Morin transition of 362 Kelvin that it's a little bit above of what we measure in the squid. So maybe the transition is a little bit more complicated than the one that can describe Landau theory, and then something else is happening. And then we were like, okay, so maybe this can be interesting. Maybe this is just a nice using of the cryostat, so we just continue measuring. Just to notice by the end of this slide, I want to tell you like about like how was like measuring this like, longitudinal resistivity. So the longitudinal resistivity of the sample was like varying a lot with the temperature as we expected, and I show you in the in the first slide when you dope it, and then you have a jump in the behavior. You have a jump, and this jump it's like also consistent with the Morin transition that is predicted by the Landau theory. That was just a curiosity. And then, so we have like, so we patterned some hall bars, and then we were like, okay, so what happened with the crystal direction? So we have like some symmetries of the altermagnets, and then we want to explore these altermagnetic properties that predict that the symmetry and the signal of the anomalous Hall effect will depend on the direction of the crystal. So in all the cases, if you plot a hall bar and then you pattern it in your material at different angles, if I am like this and my sample is changing from easy axis phase to a basal plane, I don't care if I am looking there, if I am looking there, I will just see like some nil vector just going up, going down, right? So it doesn't matter the orientation of the hall bar, it will feel the same spin reorientation. So we will, in principle, if the altermagnets were not planted by Libor and we were living in a happy world of only antiferromagnets, we will not expect anything. But what happened? Well, you say boring, I say more time. And then what happened? So when we measure along the a-axis, we have like this antisymmetric signal that I measured before, but then we pattern something at 45 degrees, and then we have a totally symmetric signal. So that was surprising, because we passed from a fully antisymmetric signal to a fully symmetric signal. And you will tell me like how fully symmetric signal. So we just plot the symmetric part, and then you see like, well, like the graph at 45 degrees, it's like more symmetric than the one at 0 degrees. And then when we plot the antisymmetric part, you have like a huge contribution in the symmetric part when the whole bar is patterned along the a-axis. So we repeat this experiment with other angles, and then when we pattern again like another a direction, we have a similar graph. And then when we pattern along 45 degrees, we have like the blue one, and then when we have the minus 45 degrees, we have the purple one. So it's similar colors because this is just a mirror reflection. So we were expecting also that mirror reflection. Well, Libor was expecting that mirror reflection. I was like, when I was measuring, just really confused about what we were measuring. And then when we measure between these two angles, so between like more or less between these two angles, between the fully symmetric and the fully antisymmetric signal, we have almost null signal. So you have a almost cancellation of this anomalous Hall effect. So I will promise you more details of all the measurements next week, that the paper will be with an archive code. For now, you just can discuss with me. And then we have, so this symmetry of the signal follow the symmetries of the crystal. So we have a fully symmetric signal when you have iron, oxygen, iron, and you have a fully antisymmetric signal when you have iron and then like another iron here. That's quite curious. And then that can only be explained by the altermagnetism that Libor explained. So as a conclusion and perspective, I think I was like too fast maybe. I would like to conclude that we need to have conductive hematite. It's necessary to prove the altermagnetic transport properties. That we have the crystal Hall effect that is only present in the low temperature phase. In the easy plane phase, we don't measure any crystal anomalous Hall effect. And then the crystal orientation, the crystal orientation dependent Hall signal was quite high. So we have different symmetries depending on the symmetry of the crystal for the signal. And then, that's the last conclusion. That the signal symmetry follows the signal of the symmetry of the crystal. So thank you so much for your time. I am just more than open for discussions, and I will use a lot of Libor here to answer all the questions that I cannot.